Okay, in this video I'm just going to look at some of the characteristics of different types of polynomials. So we'll start with your linear polynomial. That would be a polynomial of degree 1, not degree 2. So degree 1, n equals 1. So that's of the form mx, f at x equals mx plus b. So you know that that's a straight line. So there's sort of two ways I could look. It could be going up like this. So that would be a positive slope, and going down like this. It could be different, y-intercepts, so it could be different sort of positions, but it's always going to be going up or down. And you should know that the way you will know which of these happens is all based on this m value, or we called it the slope, in grade 9 when you learned about linear functions. But now we're going to refer to it as the leading coefficient, because it's the coefficient of the variable with the highest power. And in this case, the highest power is just the 1, which is our degree. So if m is positive, then we have a slope like this, positive. And if m is negative, then we have a negative slope, and it will be going down. So let's just go through some of the properties we talked about looking at with functions. So things like end behavior. So the end behavior is different for these two examples that I drew. The end behavior really just depends on what your leading coefficient is. So if m is bigger than 0, there's going to be one type of end behavior, and if m is smaller than 0, there's going to be another. Remember, end behavior tells us what happens as x gets very large, and what happens as x gets very negative. So in this case, the m bigger than 0, the positive m, as x gets very large, this function gets very large also, right? The arrow is pointing up, and the y value is getting bigger and bigger and bigger. So that tells us that f at x is going to infinity. As x gets very negative, so as we go in this direction, we're traveling along the function this way, and we're going down and down and down, so f at x is getting very negative. So that's the end behavior for a linear function with a positive slope or a positive leading coefficient. If it's a negative coefficient, the end behavior is going to be just the opposite. As x gets big, the function goes down. So our end behavior is that f at x goes to negative infinity. The y values are getting smaller, or more and more negative. And just the opposite as f at x goes to negative infinity. As we go in this direction towards negative infinity, f at x is getting bigger and bigger and bigger, larger and larger y values, so we're going to infinity. So that's our end behavior of a linear function. So it depends on the leading coefficient. You're going to see end behavior always depends on the leading coefficient of the function. Zeros. So zeros is just another word for well, if we're thinking about the graph, we'll think about this as x-intercepts. Zeros is usually what we're talking about when we're talking about the function. It's a zero is when does f at x equal 0? So for which values of x? Now in a linear function, notice both these examples, there's one x-intercept. There's one value where f at x would be 0. And that's always going to happen. So there is 1 0. Okay. So notice that for a linear function of degree 1, there is 1 0. So notice those numbers match up. As we go through the higher degree polynomials, you're going to see that pattern continue. So degree 1, 1 0. Not a coincidence. And the final thing we're going to look at is turning points. So you have to remember what a turning point is. A turning point is when a function changes from increasing to decreasing. Well, notice this linear function is always increasing, right? It's always going up from left to right. And this one is always decreasing, always going down from left to right. So if neither of these ever changes from increasing to decreasing or decreasing to increasing, there are no turning points. So there are 0 turning points. So notice again, the degree is 1, but we have 1 fewer turning points. So for a degree 1 polynomial, there is 0 turning points. And you'll probably notice a pattern as we go through. Okay. Next one we're going to look at is quadratics. Okay, so quadratic functions. So quadratic functions are of degree 2, so 1 higher degree than linear. General form, f of x equals ax squared plus bx plus c. So here's a couple quadratic graphs or parabolas that you would be familiar with. So we can have ones that open up or ones that open down. What does that tell us about the end behavior? Well, remember, it opens up if that leading coefficient, the number in front of the x squared, is positive, and it opens down if that number is negative. So the leading coefficient is going to tell us about end behavior. So as x goes to infinity, and as x goes to negative infinity, for a quadratic with a leading coefficient that is positive, the function is going up and up and up, meaning f at x is going to infinity. The same for negative values. So as you go along in the negative direction, we're going up and up and up towards infinity. So the end behavior is the same in both directions. For an a value which is negative, so this is a parabola opening down, would have just the opposite. So as x goes to infinity, so as we move along the parabola in this direction, so we're moving along the parabola this way, we're going down and down and down, so f at x is going towards negative infinity. It just keeps getting larger and larger in the negative direction. The exact same thing happens on the other side of the parabola. As you go towards negative infinity, this direction, we're going to go down and down and down, so y is getting more and more negative, so we're going to negative infinity. So the end behavior on both sides is going to be the same. But if it's opening up, then you're going towards infinity on both directions. If it's opening down, then you're going towards negative infinity in both directions. Zeros. The zeros of a quadratic. Well, in this case, I have 2 zeros. One here, and in this case I also have 2 zeros. You may or may not remember that you won't always have 2 zeros. You could have it such that the parabola just touches the x-axis, so the vertex is right on the x-axis. So you have 1, 0, or you could have it so that it was opening up and above the x-axis, so something like this, so it never crosses the x-axis, or it could be opening down and be below the x-axis, so never crosses that way. So you could have 2 zeros, you could have 1 0, or you could have no zeros. So 0, 1, or 2. But what we want to focus on is there is at most 2. So at most 2 for a degree 2 polynomial. So remember, the degree is 2, and you have at most 2 zeros. Remember, for a linear, the degree was 1 and there was 1 0. So it's not a coincidence that those two numbers match up. But what it also is important is that you might have fewer than 2 for a quadratic, whereas a linear you had to have the 1. Turning points. A turning point is where we change from decreasing to increasing or increasing to decreasing. And for a quadratic, that's just going to be the vertex. Right? The vertex is where we switch from increasing to decreasing or decreasing to increasing. No matter what quadratic you have, there will always be, there is one turning point. Okay. So for a degree 2 polynomial, so the degree is 2, you have one fewer than that many turning points. So you have one turning point. Remember with linear, degree 1, linear was degree 1, you had one less than that many turning points. So you had 0 turning